Hi everyone. Today I'm going to talk about fine-tuning large language models, and this presentation is aimed at targeting from beginner to advanced level. So I have designed the slides in that way. Let's go through this. The first one, I would like to discuss what is large language model. So you can think of it as more of a neural network-based architecture, specifically the transformers. It is introduced in Attention is What You Need in paper, which is in 2017. So this is the architecture which is used in the large language model, which we currently use. And what we do here is we pre-train our neural network architecture on a large set of corpus, which is internet scale of data. Maybe you can think of books, code, and publicly available materials. So through this process, we make the large language model understand the pattern, language pattern, and specifically, we make the model to good at predicting the next word token. And if someone is starting today freshly, I would highly recommend they go through the paper. Attention is all you need so that they can understand the architecture better before they dive into the coding part. So the next one is evolution of LLMs. LLMs or the next word token prediction is not something new. It has been in for decades now. So initially, it started with n-gram prediction, which basically uses statistical models to guess the next word based on the limited context. Then it comes the recurrent neural network. If you look at your mobile and if you used WhatsApp or iMessage before, it when you type few words, it suggests the next word. So basically, it's using the recurrent neural network model. But the problem with those models, it's not able to pay attention to a long context, and that's where the current LLM excels at. So with the help of self attention, the large language model is able to pay attention to a long context and able to produce coherent text message. So this is what all of the current modern LLMs is using. The next one is what is pre-training versus fine-tuning. So as I said in the beginning, LLMs are a neural network architecture which are trained on internet scale of data. It's more of a unsupervised learning. So anyone who familiar with machine learning, they might have very much know about supervised and unsupervised learning. So here we do pre-train the neural network architecture on a large scale of data, internet, textbooks, code. So the goal here is to make build a general language understanding and broad capabilities. This is more resource intensive process, which means it requires typically a big GPU cluster, and also it needs weeks and months of time to pre-train your model. Examples of pre-trained models, which includes GPT-4, Claude, Gemini, or whatnot. Uh, then what is the fine tuning refers to? So you have a pre-trained model, which is very good at language understanding. But when you apply that pre-trained model specific to your domain, it may not be able to perform well at the task because that pre-trained model may not well adapt to your specific task. So that's where the fine tuning comes in. Maybe I could give one example. uh, in case of Walmart, there is a brand called Great Value. But in general text, the word great value means something is available at high quality with low price. So if a customer asks LLM, can you suggest me some great value snacks? The model will recommend something of good quality with lower price. But as a Walmart customer, I would expect it recommends something of the brand great value. So in order to adapt your model to a specific domain, you need to do fine tuning on your specific data set so the model understands the pattern in your data set. So that's what we currently do with the fine tuning process. Why do we need fine tuning? As I said, LLMs trained on general data might lack knowledge or nuance for the specialized fields, medicine, law, finance. So a general LLM, if you ask something about the medical related questions, it may say that, okay, uh, consult a doctor or check with this website. But if you fine tune your model on Mayo Clinic Q&A data set, it's able to understand the medical domain better and able to respond. But even in that case, it will respond with some caution because it's medicine related one. The same will apply to the legal confirmation also. So what you will prepare a legal data set and you will fine tune your model on the legal specific data set. The advantage here is, unlike the pre-training, which requires a big GPU cluster with hours and with days and days of fine pre-training, the fine-tuning process is relatively cheaper. And also, it tailors the output tone and behavior specific to your organization and also for the user preferences. Okay. If there are alternatives to fine tuning, yes, definitely there are alternatives. So I always recommend, if your model is able to perform the task which you have with zero prompting, with zero shot prompt, it's definitely helpful to go with the zero shot prompting instead of spending time on fine tuning. The reason being, with fine tuning, you need good labeled data. If you don't have a labeled data, and also if you don't have a GPU resources, it's very difficult to go with the fine tuning process. And also, of course, you need uh, uh, deep knowledge on how to fine tune, what parameters you have to change to have a better results. So everything is determined by your use case. If your use case demands the general pre-trained model performs well on your task, you can go for zero shot learning. So this is more like, you ask the model, can you give some quick inexpensive, um, s- can you translate this specific sentence to French or Spanish? The general pre-trained model is able to perform well. You don't need to fine tune the model to perform well on language translation. This is one example. So wherever you have the pre-trained model performs well without having fine tuning, you can go for it. The next one is few shot learning. As part of your prompt, you can provide examples so that the model can understand how to respond to the user queries. So one thing is, as part of your prompt, you can provide few examples like, okay, classify this category, and then you can give, this is the sentence and this is specific category. So the model learns from the examples which you provide in the prompt, and then it responds to your questions. So this is one good alternative. If you don't have enough sampled enough label data, I highly recommend to go with few shot learning. And even we have seen very good performance with few shot learning in our experience. The next one is the retrieval augmented generation. Assuming that your underlying data is going to change frequently and you need a real-time retrieval of data, then definitely it's advantageous to go for retrieval augmented generation. It has a big advantage. It combines both the retrieval system along with the language generation system. So if your underlying data going to frequently change and you need to retrieve the fresh information every time when the model is prompted, it, it's highly recommended to go with retrieval augmented generation. And with retrieval augmented generation, the one caution I would like to make, you have to uh, pay more attention to your retrieval model. So as long as the retrieved content is good, the quality of the response from your language model will be better. So that's how we have seen when to choose what, the zero shot learning, few shot fine tuning RAG. So if you have a general question and answering, then you can go for zero shot method. And if you want to provide few examples to customize the response specific to your use case, you can go with the few shot by providing in prompt, in context info examples as part of your prompt. The fine tuning, if you want your model to understand your domain, then definitely go for fine tuning. And if your underlying data is going to frequently change, it's advantageous to go for the RAG, a retrieval augmented generation. So within the fine tuning, we have different methods of fine tuning process: supervised fine tuning, instruction fine tuning, reinforcement learning from human feedback, parameter efficient tuning, and domain adaptive fine tuning. The most common which we use, supervised fine tuning. Here you train the pre-trained model, which is GPT-4, Llama, Gemini, or Mistral, or whatnot, on the labeled examples where each input is paired with desired output. Think of a e-commerce platform where they want to accurately categorize millions of diverse product to simplify customer navigation. So here we have a label data. The assumption is we have a label data which says that the input is men's slim fit jeans, blue denim, size 32, and the output is cloth and apparel, and it belongs to men's clothing and it comes under the jeans. So if you have such a label data set, you can fine tune your pre-trained model on this data set, and you so that the model learns how to accurately classify the categories. This will be used for your production use case. Why it is useful? It's accurate and consistent with the product categorization, and also it improves the accuracy of the search results. And this will be preferred approach if you have a label data, if you have budget to curate examples where you can generate the label data. The supervised fine tuning is the preferred approach. And this supervised fine tuning is not something new with the, it's not something specific to large language model. This approach has been used quite common across all of the neural network architecture. So what we do traditionally, we freeze all of the model layers. So what you see here is a simplified version of LLM architecture. You have input input from coming from the user, and which translates to an embedding. And we have a set of transformer blocks, that it's not just a single transformer block. We have a set of transformer block followed by the output layer. What we typically do with the neural net based system, we freeze all of the pre-trained, all of the layers except for the last one, so that we fine tune only the last part of the pre-trained model by adding a classification head on top of it. This approach is much faster. The advantage is it's quicker to fine tune because we add a classification head and only update the parameters, update the weights of the last layer, and we do not touch any of the previous layers. We freeze them. If you want more performance, definitely you can try with unfreezing few of the last layers, but it's a trade-off between your performance versus the uh, time required for the fine tuning. The next one is the instruction based fine tuning. So here the we train the pre-trained model to follow natural language instructions and generate helpful contextual response. So let's say you have a retail customers which frequently ask personalized questions such as product recommendation tailored to their specific queries. So here we fine tune the model using the data sets with clear instructions. For example, the instruction here, recommend affordable wireless earbuds, which is 50 under $50, suitable for workouts. So the model will output SoundMax wireless part earbuds, which is $39, and whatever the other products which is lesser than the budget. So here the goal is to make the model follow the instruction provided by the user. So for that we need two things. One, we need to choose the model which we are fine tuning as the instruct based model. If you look at the Hugging Face, for the list of models available for Mistral, we have Mistral base model, and also we have Mistral instruct model. So if your use case requires the data to be fine tuned based on the instruction from the user, then I would recommend to choose the instruct based model and then also prepare your input data in such a way it contains the instruction to be followed, so that the model uh, learns to follow the instruction and produce better results. The next one is the reinforcement learning from human feedback. Here, we train the model to improve its output based on the human preferences and ratings of its responses. So here, retailers use chatbots to handle customer support queries from returns, refunds, and shipping problems. So each time when the model responds, based on the output, based on the which output or which response the user picks up, the model learns to update its parameters, and then when the next time when the user asks, it responds in a positive way. So here, for each of the positive response which the model gives, there will be a reward system that gets added, so that the model learns how to respond based on the human feedback. This is particularly useful for any chatbot kind of application. So, for example, here the customer query is, I received a damaged item. Can I return it? Model response gets rated by whatever the model response, which gets rated by the human raters, and then which is used by the model for the uh, uh, retraining process or or the learning process. Parameter efficient fine tuning. Uh, with large language model, I would say this is the most preferred method for the fine tuning process. The reason being, as you've seen before, with the traditional fine tuning, we only fine tune the last layer of the model by adding a classification head. It is advantageous. The reason being, it's very quick. We do not touch the other layers. But in parameter efficient fine tuning, we inject a low intrinsic matrix across all of the transformer blocks. Here, we not only fine tune the last layer, but also we inject a low intrinsic matrix across different transformer blocks, which helps to update the weights across di- entire transformer blocks. So the model adapts well to your label data. And this method was introduced by Microsoft researchers back in 2021. And it decomposes the matrix into two smaller weight matrix. And also, it not directly updates the model weights. Rather, it updates the uh, gradient, which is like a sorry, it updates the delta weight, which we are going to make changes to the original one. uh, and also with the delta weight, it's not directly updating that one, it's decomposing it into a two smaller matrix and then updates the parameters. uh, this is very fast, and also this also has better performance. The reason being, it not only it we have the flexibility to inject this across multiple transformer blocks. So as I said here, we have a LLM architecture with earlier self-supervised fine-tuning. We attached a classification head only to the output layer. But here, what we are doing is we are injecting the low rank adaptation matrix across the different transformer blocks. And then we are updating not the original weights. The original weights will be frozen as it is, but the up delta to the original weight will get decomposed to a two trainable smaller matrix, and then it gets updated. That's why this method is getting more popular. And also this is more efficient in terms of the performance and the time it takes to train. Domain adaptive fine tuning. So this is more like fine tuning that adapts a general purpose language model to understand the industry specific terminology, context, and user behavior. For a general language model, the word apple means it could be a fruit. But for a retailer, they might expect when they want to buy apples of Apple product, it might refer to the phone, actual phone. So he- It helps the retail search engines to accurately interrupt the customer intent to deliver high relevant product results. So in the beginning, I provided the example of great value product, and the same one here applies. So when the customer queries cheap running shoes woman, the general model might focus on running as its activity. The adapted model understand retail context, cheap, which implies uh, the budget friendly options. Women refers to the product category, and ordering of the terms indicates the priority. So it provides the results which prioritizes affordable women's running shoes rather than general information about running. So this is useful because it significantly improves search relevance and customer satisfaction. Also, it helps the customers to maintain competitiveness in accurately interrupting the customer intent. So next, we will go through the process on how to perform fine tuning. So the first and foremost thing is to define your task and choose the base model. And the next part is prepare your data set, perform fine tuning, evaluate the and optimize the model, and deploy and monitor. We will go through each of the steps. Okay, here the goal is to define your task precisely. So the your task dictates whether you need to go for fine tuning, or you need to go for a RAG, or you need to go for a zero shot learning or few shot learning. So you have to accurately define what you want to perform. So in this case, we are going to classify the product reviews descriptions into product categories. Then comes the right choosing the right base model. We have a lot of open source models and also the closed source OpenAI models available. So which model we have to choose for the specific task at hand? The choice of the model depends on your latency constraint, the performance, and also the task at hand. uh, Large models will perform based on our experience. uh, if you use llama 70 billion model, it gives a better performance, obviously the most better performance than the llama 8b or 1 billion model. But it comes at the cost of your latency and also the number of gpus required to fine tune. uh, so while choosing the base model, you have to look at the performance, whether uh, the proven results on similar classification task which you are working, how quickly you need response, and also how much GPU you have, and how much GPU that specific chosen base model require to run. Uh, Considering all of this, you have to better identify the best model for your best base model for your use case. And you can go to the Hugging phase, and you can choose your model by filtering by task, text classification, product categorization. So it helps you to choose the right base model for your use case. Then you have to prepare your data set. In this example, we are loading the data set from Hugging Face, Amazon US reviews, and then we convert to a instruction based fine tuning format by uh, formatting your input columns in such a way that it follows that instructions. So classify the following product reviews into a category. Input is what we get from the data set, and output is also the label from the data set. We form it more as a instruction based on the input features available in the data set. Then you split your data in the same way. The next process is tokenization. Once you have the data prepared, you tokenize the data using the different tokenization available. It's model specific again. The common tokenization method is sentence piece tokenizer, where the text is converted into a like where the given text is converted to a subwords, and then each token ID is assigned. It handles the vocabularies which are not in the words which are not in the vocabulary by splitting it into a breaking them down into meaningful parts. So that's the one advantage with sentence piece tokenizer. But we have different uh, bits and piece tokenizer by bits and bytes tokenizer available. And also we have recently byte uh, I believe it's 1 byte encoding. Tokenizer also recently introduced. It performs really better. It also depends on the model which you choose. You don't have the flexibility to choose uh, one base model and choose a different tokenizer which was different from what is used in the model. It is strictly tied to the model which you are choosing. And fine tuning versus parameter efficient fine tuning. In full fine tuning, what we do, we update the parameters of the entire model. It will be really helpful when you are going for a domain specific foundation model. Recently, Netflix, Meta, they come up with a full fine tuned foundation model specific to their use case. Netflix for predicting the next movie which the user is likely to click or watch, and Facebook for the ads data. So what they did is they prepared a new foundation model specific to the use case. So if your use case requires full adaptation of your model to the data, then to your domain data, full fine tuning is performed, and this is more time consuming. But also here we update the parameters of the model entirely. The next one, as I said, the parameter efficient fine tuning. We have different method in the parameter efficient fine tuning: LoRA, QLoRA, and then the adapters. It's much lower computational resources needed, and also it's fast in the training process, and it requires less memory. Challenges: it has slightly reduced performance compared to the full fine tuning. It's a trade off which we have to choose between the time we require for that fine tuning process versus the results. Yeah. Thank you. That's Thank you for listening to this, and hope you enjoyed the presentation.